Good morning. We have four lectures left and they're all on applications. And the first lecture deals with iron and steel applications. And then we'll do some other applications like non-ferrous, which is aluminum, glass, mineral processing, ceramics, and petrochemicals. So we'll cover a lot of the main applications. But today is iron and steel. VF is a blast furnace. BOF is the basic oxygen furnace. EAC is a electric arc furnace. And then AOD is the argon oxygen decarbonization furnace. So we'll go over these four applications and we'll look at the kind of refractories that are used. And then I have post-mortem studies. And I actually have one study today on an electric arc furnace. So we'll look at what happens to these refractory microstructures during use. So if you're not familiar with a steel plant, this is basically a diagram showing an integrated steel plant. The iron making is done in the blast furnace, and you have your iron ore, your carbon source, which is coke, and the limestone to make the slag. That goes into a blast furnace that makes the iron. The iron is transferred through some type of hot metal car to a basic oxygen furnace, and that blows oxygen into the iron and removes the carbon. You also have electric arc furnaces, which melt scrap. And so the steel, either from a basic oxygen furnace or an electric furnace, goes into a ladle. And the ladle may just be used to transfer the steel, or you can do some type of secondary refining. And then from that ladle, you either pour ingots or go to some type of continuous caster. So that's an integrated steel plant. So we'll go over the blast furnace, the basic oxygen furnace, the electric furnace, and a little bit on ladles, the ton dishes here, the slide gates, and even this hot metal car. Plus, we'll do the argon oxygen decarbonization vessel for making stainless steel. So the blast furnace that produces iron. So there are various iron ores, Fe2O3, Fe3O4. This is Fe2O3, but it's hydrated. This is an iron carbonate. The impurities are usually alumina and silica. So you have your iron ore. Limestone is the calcium carbonate. That makes the slag. And your carbon source is coke. That reduces the iron oxides to metallic iron. The blast furnaces are basically large vertical cylinders. They can be quite large, maybe 200 feet high, maybe 40 feet in diameter. So they're large, basically large cylinders. The charge is fed in at the top of the furnace. There are tuyeres at the bottom that use preheated air. So that preheated air comes through the tuyeres at the bottom. It passes upward through the charge. That causes the coke to burn. That generates heat, produces carbon monoxide gas, and temperatures go as high as 2,000 degrees C. The limestone forms a slag, which sits on top of the molten metal, and the slag also removes the impurities. The CO gas that's generated reduces the iron oxides to molten iron. And then the molten iron is collected at the bottom of the furnace. It has 5% carbon in it, and the slag is floating on top of the molten iron. So these vessels last between 5 and 10 years. So the reactions that are taking place in this vessel, carbon plus O2 forms CO gas. The calcium carbonate decomposes to lime and CO2 gas. And then the iron oxides react with CO to form liquid iron plus CO2 gas. And then the carbon again can react with the CO2 gas to form more CO gas. So here you're forming the liquid iron. It has about 5% residual carbon. So this is a schematic diagram of a blast furnace. And at the top of the furnace, the charge, it enters. That's your coke, your iron ore, and your limestone. There are tuyeres at the bottom that push the preheated air up through the charge. And then at the bottom, you collect the molten iron. And sitting on top of the iron is the molten slag. And they're tapped off periodically. This is just another view without the charge. So the charge comes in through the top. Everything eventually melts and the reactions take place as it moves downward, and you end up with your molten iron and your molten slag. These are tap holes where the molten iron is removed and then the molten slag. And then these are your tuyeres for the preheated air. So this is how a blast furnace is zoned. In the top region here, you have impact and abrasion from the charge entering. In the center of the furnace, there's issues with CO disintegration because of all the carbon monoxide present. It reacts, CO disintegration is when the carbon monoxide reacts with residual iron in the refractories, forms an iron carbide, which disrupts the structure. So that's CO disintegration. There's alkali attack. There's also thermal shock. And at the bottom, you have slag corrosion and metal penetration. So at the top of a blast furnace, you're usually going to have some type of high duty fire clay. So it can be a brick shape or it can be a castable. You may also have a phosphate bonded alumina that contains silicon carbide for abrasion resistance. The sidewalls are usually a high alumina brick. And then down towards the bottom of the sidewalls, you have a higher alumina content, maybe greater than 90% alumina. The hearth is going to be a high alumina brick, plus it's going to be lined with carbon. Carbon is non-wetting for the metal. The metal is non-wetting on the carbon. So those are the different kinds of refractories that are commonly used in a blast furnace, and that's how it's zoned. The basic oxygen furnace, the iron from the blast furnace is converted to steel by removing the carbon. So the charge is the molten blast furnace iron. There's some scrap metal that's added, maybe 15 or 30% scrap metal is also added. And then you have your limestone, your calcium carbonate to form the slag. So a basic oxygen furnace is in the form of a crucible that has that can pivot. So it's a tilting crucible. It tilts to pour the molten metal and the slag. These run up to about 100 tons for their capacity. So you basically have a water-cooled lance from the enters the top of the crucible or the top of the furnace that blows oxygen into the molten iron. The carbon in the iron is oxidized, that generates heat. And these run about 1800 degrees C. And then the limestone melts and forms a slag. It takes up the impurities. Some of the impurities in the metal are also oxidized and captured in the slag. Metals like manganese, also sulfur and phosphorus. And then this furnace is rotated to tap the steel. And the carbon contents, depending on the type of steel they're making, range from 0.01% to 2.25% carbon. And then they have a process known as splashing. So this furnace is then inverted, and that taps the slag, but before they tap the slag, they rotate the furnace to splash the slag up on the sides of the furnace to cover the refractory. And that's a coating that's basically a barrier to oxygen diffusion. Because these are lined with a carbon type composite. So they try to protect the carbon from oxidizing by splashing a slag on top of the refractory. And when these furnaces first came out in the 50s and 60s, they were running less than 200 heats per campaign, but nowadays 20,000 heats is possible because of the carbon matrix composites. So these vessels have really improved their campaign lives. So basically, in this process where you're converting iron to steel, the carbon in the iron plus oxygen forms CO gas. So you're removing the carbon and ending up with steel. You're also going to oxidize some of the iron to FeO, and then the impurities are going to react with this FeO, like silicon and manganese, and some of that is going to go back as iron. So you're going to end up with SiO2 in this case plus Fe, and MnO plus Fe. And the carbon is also going to reduce the FeO to CO and Fe. Obviously, you don't want to oxidize too much of the iron. So this is the basic oxygen furnace. It's a large crucible. The pivots are on the side, known as trunnions. So it tilts. There's a tap hole for removing the iron. And then this is the water-cooled oxygen lance, where the oxygen is blown into the iron. So there's basically three versions. The first is the top-blown basic oxygen furnace. So here's your molten metal. Sitting on top of the molten metal is the slag. And here's your water-cooled oxygen lance. And that blows oxygen into the melt. So some of the slag splashes up on the sidewalls, which is advantageous. You have a lot of stirring at the top here, but not much at the bottom. Then the next version is a bottom blown converter, where you're blowing the oxygen and they're actually adding the lime for the slag through the bottom. So there's a lot of stirring at the bottom, but not as much at the top. And then this one is both top and bottom blown. So you have gases coming through the bottom and through the top. So that promotes a great deal of stirring, and the reaction to take place faster. So there's three versions here. This is a top blown BOF, and this is how it's zoned. There is slag corrosion in the top region here. There's moving slag and metal erosion in the middle here. And then at the bottom, there's hot metal. And there's also impact from the scrap that's dumped in. And when you dump in hot metal, there's a hot metal stream that's impacting the bottom, as well as large pieces of scrap metal. So the nose area here is usually a plastic refractory, like an MgO-based material. The tap hole is usually a plastic. It's an MgO carbon composite. There's a safety lining, the outer lining, and that's MgO, and it's in brick form. And then the working lining is the MgO carbon composite, and that's in the brick form. And these are quite thick, 3 or 4 feet or more. So these are really, really thick linings for the MgO carbon composites. And then the same issues here for a bottom blown basic oxygen furnace, slag corrosion towards the top, moving slag and metal erosion in the middle, and hot metal and scrap impact on the bottom. So the lining is basically the same, except now the bottom has a removable bottom, and that's the in brick form, and it's the MgO carbon composites. So here's where the gases are coming in through the bottom. And then the one that's top and bottom blown, again, it's the same issues, slag corrosion, moving slag and metal erosion, and then hot metal and scrap impact on the bottom. Same type of refractories on the lining, except now on the bottom, you have these porous plugs. So they're bricks and they're made out of MgO, so they're very porous. So the gases go through the pores and stir the melt in the bottom. So you can see all the different kind of refractory compositions we've discussed are used in all of these vessels. The electric arc furnace is basically melting scrap and making different alloys. So the charge is a scrap metal. Various other metals are added to make alloys like Cr, Ni, Mo, Ti, and V. And then you have your limestone for the creation of the slag. So this is a crucible, but it tilts, and it also has a removable roof, and they can be quite large, up to 100 tons capacity. So the heat is generated by 3 carbon electrodes, and you strike an arc between these electrodes, melt the scrap metal, and the temperatures reach about 1800 degrees C. Again, the molten slag forms from the limestone and whatever impurities are present. And if you have a great deal of carbon present in this scrap metal, you can use a water-cooled lance again to blow oxygen into the molten metal to oxidize some of that carbon. Again, you can oxidize and capture impurities like manganese, sulfur, and phosphorus in the slag. And then the furnace is rotated to tap the steel, again, 0.01 to 2.25% carbon. The removable roof is to allow the charge to take place. So basically you're melting scrap metal, but if you're oxidizing carbon, it's carbon plus O2 forming CO gas, just like in a basic oxygen furnace. So this is a side view of a electric arc furnace. Here are your 3 electrodes. Well, you can only 2 are shown here, but there are 3. Here's your roof. That roof lifts up and rotates out of the way, and then the charge is dropped in. And here's a tap hole for removing steel or slag. So this is how the furnace is zoned. There's thermal shock issues on the roof and upper sidewalls. When you get down to where the slag is, there's slag corrosion issues. And you're dropping in scrap metal, which could be an automobile that's been crushed into a cube. I mean, there's really, really large pieces of scrap metal being dropped in. So there's impact issues. This roof can be either brick or castable. It's usually high alumina. And then there's 3 holes in the roof for the electrodes. Upper side walls may be a mag chrome type material. The bottom may be an MgO brick. And where there's a slag metal line, where there's the most corrosion taking place, you may have an MgO carbon brick. And the bottom maybe an MgO ramming mix. The AOD vessel, argon oxygen decarbonization furnace. That's where you make stainless steel. The charge is usually a scrap metal. It can also be metal from an electric arc furnace, molten metal. And you add ferrochrome because you're adding chrome to iron to make the stainless steel. You're adding limestone to form the slag, and a fluorospar, calcium fluoride, is fluxing the limestone, making it more fluid. So it's a similar design to a basic oxygen furnace. It's a tilting crucible. Again, they can be quite large, maybe 100 tons. And then you have your water-cooled lance coming in through the top, but you also have tuyeres in the bottom, and they're blowing mixtures of oxygen, argon, and nitrogen into the molten metal. So carbon is oxidized when you blow on oxygen. That generates heat, maybe up to 1800 degrees C. And then when you're blowing in argon and nitrogen, you're taking any other chrome oxide and you're reducing it back to chrome. So when you blow oxygen into the furnace, you're oxidizing the chrome. You don't want that to happen. So then you blow argon and nitrogen to put that chrome oxide back into metallic form, into the metal. The slag forms from the limestone and the fluorospar. And again, impurities in the metal are oxidized and captured in the slag, manganese, sulfur, and phosphorus in particular. And then this furnace is rotated to tap the steel and inverted to tap the slag. So if you're running oxygen, high levels of oxygen, that removes the carbon. So carbon plus oxygen forms CO. It also oxidizes the chrome to Cr2O3, and that ends up in the slag. But then when you're running high argon and nitrogen levels, that's going to reduce this Cr2O3 back to Cr. So Cr2O3 plus carbon in the iron forms CO, and then the Cr is back into the metal, so to form stainless steel. So this is a side view of a AOD vessel. You have a top lance that can blow oxygen, argon, and nitrogen. And then there's a tuyere in the bottom that can also blow argon, oxygen, nitrogen, or air. That also stirs the melt also. So this is how one of those vessels, the AOD vessel, is zoned. You have slag corrosion and thermal shock issues in the top. You have moving slag and metal erosion issues in the middle. And again, you're either loading scrap or hot metal, so there's impact on the bottom. So the top portion of this vessel, the hood, is usually a mag chrome brick. And then there's a working lining and a safety lining. The safety lining is usually a mag chrome brick. And then the working lining is usually a mag chrome brick or even a dolomite brick. Dolomite works rather well here. It's a good high temperature material. And then the bottom is a mag chrome brick, but it's usually a higher quality, so it's a fused grain, much more dense grain is used in the bottom. So that's what an AOD vessel looks like. I showed a hot metal car transporting iron from a blast furnace to a basic oxygen furnace on the first slide. So these are cylindrical shapes with conical ends, and the capacities range from 125 to as high as 250 tons. And that's just collecting the molten blast furnace iron and moving it to the basic oxygen furnace. So this is what a hot metal car looks like in schematic drawing. You have slide corrosion issues because the slide comes along with the metal, and metal penetration issues. You also have thermal shock issues when you pour hot metal into this. So it's basically a cylinder, conical ends. You're going to use a pitch infiltrated high alumina refractory. So it's a fire brick with pitch or pitch infiltrated high alumina, or it may be a resin bonded alumina carbon refractory, one of the composites. The ladles move steel from basic oxygen furnace or electric arc furnaces to where they're cast into ingots or continuous cast ribbons. So they're also just carrying molten steel. So they're basically crucibles, large crucibles, and they can do additional refining in these ladles. There may be a deoxidation step, maybe a vacuum degassing, maybe more sulfur is removed, maybe their alloy additions are made to make alloys, and there may be a gas for stirring through a tuyer. These may last up to 100 heats. So there's various designs. This is just a transport ladle used for transporting and pouring steel. There's obviously thermal shock and corrosion issues in the top, and thermal shock and erosion issues in the bottom. The top area is known as the freeboard. That's usually a MgO CR203 magchrome type brick. There's a backup lining, which is an aluminum brick, and then a working lining, which is a high alumina brick, usually one that consists of mullite. There's a porous plug in the bottom for stirring to allow gases to stir the melt. So that's usually a high alumina brick. And then there's a well here where there's going to be a slide gate for controlling the flow of metal. So there's a well block, which is usually an alumina chrome. The chrome is added to improve corrosion resistance. This is what a refining vessel might look like. Again, there's thermal shock, and you're going to have carbon-based material, so there's an oxidation issue. Again, thermal shock, oxidation, and corrosion towards the middle, and thermal shock and erosion in the bottom. So the metal is going to sit in a refining ladle more than just in a pouring ladle, a longer amount of time. So these are backed up with an insulating lining. They could be IFBs, insulating fire bricks, or fiber boards. Then there's a backup lining, maybe an MgO or 203, a matte chrome brick, or an alumina brick. And then there's the working lining. It's going to be an alumina MgO carbon material. It can be brick shape or cast. And in this system, I mentioned there's going to be spinel formation during use. There's going to be a porous plug and a well block. Again, the porous plug will be high alumina, a porous high alumina refractory, and then the well block would be a brick on alumina enriched with CR203 to improve the corrosion resistance. And then the slide gate is a gate that controls the flow of the molten metal. It's going to be at the bottom of a ladle or a bottom of a tundish, which I'll describe in a few minutes. And these are going to control the flow of the molten steel. So this is a schematic diagram. This is the bottom, basically, of a ladle. Here's your well block up here, and then your slide gate is just below the ladle. So there's a fixed plate with a hole in it, And then there's another plate that slides with a hole in it. And when the holes are aligned, metal flows. Then when the holes aren't aligned, it stops the flow of metal. So here's your fixed plate, here's your sliding gate plate, and then there's a nozzle or tube at the bottom to control the flow of the metal. So this is your well block in the bottom of your ladle. And again, I said usually an aluminum chrome material. It could also be a high aluminum material. Here's your fixed plate, and then here's your sliding plate. So these plates are subjected to thermal shock, and they're composites, so they have carbon, so there's oxidation issues, there's corrosion issues, there are erosion issues from the flowing metal. So they're going to be a composite, usually an aluminum carbon composite, or if you have enhanced corrosion resistance, an alumina zirconia carbon composite. Both the sliding gate plates and the nozzle here. And then the tundish controls the flow of molten metal to the continuous caster. It's also picking up and trapping refractory inclusions, and it has a slide glader also. So the charge is molten steel, whether it's from an electric arc furnace or a basic oxygen furnace. The tundish has to retain thermal energy, so it has to be insulated. And it has an inert barrier between the molten steel and the permanent lining. So there's also a slag present, and that's trapping inclusions prior to continuous casting. So these inclusions are low density relative to the metal. So inclusions might be 2 to 3 grams per cubic centimeters. The molten metal is 7 grams per cubic centimeters. So there's a flotation process where the inclusions float up out of the metal into the slag. So these have a permanent backup lining and then a renewable working lining or a disposable working lining. So the tundish, you want to have it insulated so that the steel retains its temperature, and you need a chemically inert barrier between the molten steel and the permanent lining. And that allows for a parting plane when the spent lining is removed after you cool it down. The spent lining parts are easily from the backup lining or the permanent lining. So this is a ladle with the molten steel. Here's your slide gate and your tube that controls the flow of metal. This is the tundish. It's sort of like a bathtub shaped vessel. There's another slide gate below that and a tube, and that controls the flow of metal into your mold here, and then you have your continuous caster. So that's the arrangement. So here's your tundish. Here's your tube from the ladle controlling the flow of steel. Here's your tundish. And then here's another slide gate. There's a slide gate here. And here's another tube going into the continuous caster. So the tubes, you're flowing hot metal through these. So there's a thermal shock issue. They're made out of these carbon-containing composites. So there's an oxidation issue and corrosion and erosion because of the moving metal. So here's the tundish shrouds, and here's the ladle shroud. They're all going to be composites, whether they're alumina carbon, alumina zirconia carbon, or alumina silica zirconia carbon. They have to be thermal shock resistant and corrosion resistant. And then the tundish itself has a renewable lining. So there's basically a thermal shock issue here. They're not worried too much about corrosion because the lining is renewable. So there's an outer backup lining Usually an insulating brick or castable, high alumina, 50% alumina. This blue area actually has two linings, an outer backup lining and an inner backup lining. So the inner backup lining is a denser brick or castable, higher in alumina content. So these are the permanent linings. And then the inner lining is the renewable lining. And there's various possibilities here. It could be a dry vibratable, magnesia olivine, so it's a high MgO content, maybe 90% MgO. It can be an insulating fiberboard, maybe 90% MgO again, maybe a magnesia olivine type composition. Or it could be a gun lining, again, at 90% MgO based on magnesia and olivine. So it can either be a dry vibratable, a fiberboard, or a gun type material. And then there's some refractory furniture in here. There's usually a pouring pad where the metal is poured into this tundish. You don't really want to pour it into this porous insulating lining. And that's usually a high alumina pad. So these renewable tundish linings last about 10 heats, let's say, and then the tundish is cooled down and it parts rather easily from the backup lining, and then a new lining is put in, whether it's one that's vibratable or a fiberboard or a gunning mix. So the last thing I have here is a postmortem study. And this is an MgO carbon refractory brick that came out of an electric arc furnace. This is the actual cross section of the brick that we cut. You can see some of the coarser grains in the brick. This is the hot face, and this is the cold face. You can see there's some whiter area here. That's what's known as the decarburized zone. The carbon is gone there. And there's a slag layer also on top of this hot face. So what I usually like to do is very simple. You look at the cold face. That's usually the refractory that's still intact. And you look at the hot face and you see what happened, what the difference is, or the difference in the microstructure. So if you start with the cold face, this is a 30x magnification. This is a MgO carbon composite. So these large aggregates, there's quite a few of them, medium size and even smaller. They're the MgO aggregates. So you can barely make out at this magnification and the way this was polished, the individual crystals. So this is a polycrystalline material. It's about almost 98% MgO. There's some lime and silica and iron oxide also. And you can sort of see these black areas, they're the carbon flakes. So the aggregates are a dead burned or sintered MgO. You can see the little black spots, they're the pores, and the little white spots are the grain boundary phases. So going up to 1000x, you can clearly see the carbon, the graphite flakes. You can see delamination, that's the microcracking. So this particular flake graphite's about 98% carbon, and there's some silica and alumina impurities. These are the finer MgO grains. They're about 96% MgO. There's silica, lime, alumina, and iron oxide present. And I'm not sure, but these look very dense. So they may be a fused MgO in the fines. to improve the corrosion resistance. Then the balance here, there's a lot of finer MgO crystals. The balance is the matrix, which is the fines plus the pyrolyzed resin in the form of carbon. So if you do an EDS analysis, the purple here is the carbon. So you can see the flake graphite where it is. This is almost 100% carbon. So the lower carbon percentages that exist in the matrix don't show up that well, but there's also carbon from the pyrolysis of the resin in the matrix. The green color here is Mg. So where you see green is MgO. There's some finer particles and some little bit larger particles. So the MgO is easy to see. These are close to 100%, so that shows up very bright, but you can also see a very dull green, the really fine MgO particles in the matrix between these finer particles. And the purple is oxygen. So you can see the MgO, again, by the purple. You can see it in the matrix. It shows up a little better for the oxygen. So any region that's purple is MgO, corresponds to where the green and the purple are in the same location. And then aluminum is in yellow. That's your antioxidation agent. It's probably oxidized at this point, so it's probably Al2O3. So that shows up in the matrix. So we go to the hot phase. So the cold phase is your typical MgO carbon composite. There's a slag layer at the hot phase. I mean, this is cooled down. It's still very porous. You can see crystals have formed in the slag upon cooling. This region down here is the refractory that's still intact. Actually goes all the way over to here. So this line here is your slag matrix interface. So you can still see the flake graphite down in here. So this is part of the refractory that's still intact. So you see your coarse MgO grains. There's a very coarse MgO grain up here. And then this is a region where the matrix has been eroded away and altered between this coarse aggregate and the residual refractory here. So here's a coarse MgO grain. It's about 94% MgO. The slag is silica, lime, alumina, and then some MgO because the refractory has been dissolved into the slag. So it's a lime, silica, alumina, MgO composition in the slag. Some of the silica has penetrated the refractory, so there's a enrichment in the silica content here. So the MgO content's a little lower than it started out at. And then this corroded layer where you're attacking the matrix, there's silica, lime, alumina, and residual MgO, almost 58% MgO. So the slag has penetrated and reacted, and it's attacking the matrix, which is where all the flake graphite and residual carbon is and the fines, but you still have your coarse MgO aggregates which are resisting corrosion. And you can see up on the top here how the slag is attacking the individual crystals in this polycrystalline aggregate. You can see the slag penetrating along grain boundaries. I can show that better at higher magnification. So if you look at the carbon content at the hot phase, here's your residual refractory that's still intact. You can see the flake graphite. All of this is an artifact from the resin that's used to make the polish section. So this is not part of the refractory. It's just the resin that we use to make the polish section. It's penetrated the pores of the slag. It holds the material together so we can polish it. So here's the MgO in green. You can see the large MgO aggregate and some little bit smaller ones here. There's still quite a bit of MgO in this reacted zone here where the slag is penetrated. And you can actually see the MgO crystals up here floating out into the slag layer. And the oxygen is in purple. It highlights the MgO grains, and it's also in the slag. The darker regions are the intact refractory where there's carbon present, so a lack of oxygen. The yellow is the lime from the slag. You can see it's penetrated behind this coarse aggregate into this region here, and that's where it's attacking the matrix, the carbon-based matrix. So the lime is in yellow, so it's a high lime slag. There's a lot of silica in the slag, so the red is Si. So you can see the silicon in the slag. It's starting to penetrate the refractory in this region here, the coarse MgO particle, and it's infiltrated behind this particle and is attacking the matrix. And then this color, the yellow, is aluminum. So there's aluminum probably in the form of Al2O3 at this point. It is now in this penetrated zone here and along the hot face. So it's concentrated in those regions here. This was at one time a matrix region. It's gone now. And then here's what's left of this matrix region, but the aluminum is most likely aluminum oxide at this point. It is basically forming a barrier to further oxidation. So all of this was at 20x. If we go to 100x, this is the slag, and this is the region right here where the slag is in contact with the coarse MgO crystal or aggregate composed of MgO crystals. So the slag cools down. There's needle-like crystals. I don't think I analyzed them, but it most likely murinite or monocellite, calcium, silica, magnesia compound. And you can see these individual crystals of MgO, how the slag, the gray colored, lighter gray, is penetrating, and these crystals are starting to float out and dissolve in the slag. So the green is Mg. You can see the individual crystals, and the slag is crystallizing in between there and over here. So there's MgO dissolved in the slag. It shows up as green. And again, this is most likely murinite or monocellite type crystals because there's lime, MgO, and silica present in the slag. The oxygen is in purple. So this is an MgO. You expect the oxygen there, and then the crystals have the higher concentration of oxygen. Calcium. There's some, you can see some of the calcium penetrating the grain boundaries, but it's mostly yellow here in the slag. It appears that the crystals have a lower concentration of lime than in the rest of the slag. And Si in the slag is everywhere. And the silicon SiO2, the red here, you can see it penetrating the MgO aggregate. So here, the black regions are the individual MgO crystals. They're now separated by enhancing, the grain boundaries are enhanced when the silica penetrates. And then this yellow type color, you can see the aluminum, which is Al2O3 now in the slag. And then it tends to be concentrated. There used to be a matrix region here. So the Al metal that's added as the antioxidation agent is still there as Al2O3. So that's what's happening at the hot phase in this MgO carbon refractory. The matrix is the weakest region. It's attacked first. The carbon is the carbon from either the residual resin or the flake graphite is being removed. You have a decarburized zone. The slag penetrates there, and then the coarser MgO aggregates are being attacked by the slag. They're pretty good in terms of corrosion resistance, and this is a basic type slag, got a lot of lime in it, and MgO. So that's what I have today. Um, I'll have more applications next time, and I think I have quite a bit more post-mortem studies to show what happens to the refractories after they've been in service. So thank you for attending today, and I'll see you on Wednesday. Oh, no, wait a minute. Today's Wednesday. I'll see you next Monday. Have a good weekend then.